Hello. One last basic DTFT operation that we need to look at is how to get the frequency response from a difference equation. So, as you recall, we can express a linear time invariant system as negative AK, k equals 1 to n, y, n minus k, plus the sum from k equals 0 to m of bk x n minus k. So that's the basic difference equation form for calculating an output. But this corresponds to, if we put everything over onto one side, k equals 0 to n, ak, y, n minus k, equaling the sum of the b's times x n minus k. And remember, we follow the general convention that a0 is equal to 1, although this is not essential to this development. It's just a good reminder. So we've taken the DTFT of signals. We can take the DTFT of both sides of this equation. So find the DTFT. So we are doing the same thing to both sides. So we would expect equality to hold. So if we take the DTFT of the left side, we get DTFT of the sum 0 to n, ak, y, and minus k. And that should be equal to the DTFT of the right side, k equals 0 to m, bk, x, and minus k. As we've discussed before, the DTFT is linear, so we can take actually the whole sum operation and throw it outside like this, giving us the DTFT of y n minus k and the DTFT of x n minus k. Well, we don't know what x is and we don't know what y is. So we're just going to have to assume that we can take the DTFT, and we can, as long as there's not some strange infinite energy signal. We'll actually talk about infinite energy signals later. But for now, assuming that the DTFT exists, then the DTFT of y is going to be, or n minus k, just going to be whatever that is with this phase shift term from the DTFT properties. That's minus j e minus j omega k. Well, we still have our sum that we need to throw out here of our AKs. And we're going to get something similar on this side. We're going to get the sum, k equals 0 to m, the bk's, and now we have this e minus j omega k x e j omega. And that's from the DTFT of x of n minus k. At this point, you may see that our DTFT of y and our DTFT of x are both not functions of k, and we have a sum over k. So if you like, we can put parentheses around this part, and we recognize that as another DTFT operation. In essence, it's the DTFT of our coefficients. So let's we'll do a few things to kind of show how this works. So first, let me just write this DTFT of the AKs, and this is the DTFT of the BKs. And also, it's very common to relate this back to the basic convolution or filtering operation. Remember that if we have the input is to a system is x, the output y is the convolution of the impulse response with the system. So recall y of n is equal to h of n convolved with x of n. And we also know that if we were to take the DTFT of both sides, whoops, we get that. I don't know why I wrote it crooked, but there it is. Can we relate the same thing here? Well, we have our y, we have our x, and we have these other terms. Sure. Let's rearrange terms and say y e j omega is equal to our sum over the b terms times e to the minus j omega k over the sum over the a terms e negative j omega k times x e to the j omega. So this large fraction in the middle is our h e j omega. So we have our output, our input, and our frequency response. And the frequency response is given like that. Another way of writing this is to find, if you know the output and the input, you of course can get the frequency response by dividing the output by the input. So y e j omega over x e to the j omega is equal to h e j omega is equal to that. Now, in so thinking, don't make the mistake of putting the a's, which are associated with the y's, on top. The b's go on top and the a's go on bottom when we're finding our frequency response.